All right, hey everyone, welcome to the next session of our machine learning track at Edge Impulse's Imagine Innovators. Thank you for attending. We're super glad you're here. Before we kick off this session, we do have a couple of housekeeping notes. So first things first, if you have any questions during the presentation, please feel free to ask them in the chat. We'll have team members monitoring the chat and we'll respond to those questions as we go. At the end of the session, there will be also time for Q&A, so you can hold your questions until then if you prefer. And then lastly, if you don't have an Edge Impulse account, right now is a great time to sign up. You can head over to studio.edgeimpulse.com/sign up to get started, and we'll put that link in the chat so it's easy to find. And then you'll be able to put what you learned today into action as you build your own Edge AI models. All right, so we do have a great session lined up for you today, and it's about the importance of doing digital signal processing for feature extraction before training your machine learning model. It will be presented by Alex Elium, and Alex is a DSP, so digital signal processing and ML, machine learning research engineer here at Edge Impulse. He has over a decade of experience in signal processing and developing embedded software for edge devices. He's worked in all sorts of verticals from defense to oil and gas and many others. And I personally ask him questions all the time. He's a wealth of information. He definitely has some important things to say, and I always love hearing what info he has. All right, without anything else, Alex, over to you.
Hey, thanks, Brian. Right, like he said, we're here to talk about DSP feature extraction today. And the reason I said why bother is there's sort of this kind of misnomer out there like, well, a machine learning model can just learn everything, right? If you have enough data, it'll get the patterns. So what are we really bothering with feature extraction? Or especially if it's something complex like digital signal processing, and especially if you also need to get those complex algorithms running on a device, possibly a very constrained device. And so what I want to do today is go through a model both ways. So I think a lot of times when you hear about feature extraction, you get the answer like, well, it's better. Like do your feature extraction, the model will be smaller, it'll be better. But I don't know how often we've actually seen a model where we're gonna actually make it converge and get like good accuracy both ways, and then you're really comparing apples to apples. What's the difference? So the data set we're going to look at is from PhysioNet. It's ECG data, single channel, and it has three classes, normal, arrhythmia, and congestive heart failure. And the two different ways to attack it we're going to look at is a pure, what we call raw in studio, meaning no signal processing, no feature extractor. We're going to feed it to a 1D conv network. And then the feature extractor we're going to use today will be wavelets. And we'll talk more about what that is. So we'll explain what we're doing, kind of look at how both work. We'll look at the results and then, have some takeaways. So what is DSP feature extraction and what are the typical ways you can do this? So there's a lot of options. It can just be as simple as filtering out noise. Another really common basis for feature extractors in DSP is using FFTs, so transforming the data from the time domain to the frequency domain. You can either just look at that as a 2D map, which is the picture I have here, or you can essentially kind of max pool these rows into more of a flat bin of what was the maximum power in each frequency across a huge window of time. If you do the 2D, right, you can imagine this is like an image. So you would do image processing type models on that 2D conv. Or if you flatten it all out where you're just kind of looking at averages or maximum frequencies, then you can just do like a fully dense model. Then you can get more complicated. MFE, MFCC is a linear transformation on a spectrogram, but it basically tries to preserve more information for hearing and audio and throw away some of the higher frequency bands that aren't as important or informational. And you can even do very bespoke things. Like, for example, you could convert a PPG signal to heart rate. But today, we're going to be using wavelets. So what are wavelets? So the very first thing we should understand before we talk about it is, what is convolution? And this will be important for everything we're going to discuss. So let's make sure we've got that concept nailed down. So it's essentially a rolling dot product. So in my example here, I just have two rectangles or box cars. And what you're showing here is top to bottom. The top row is generating the first point. So at the very top right, you've got no overlap. So basically zero. And you see the zero in the bottom here. And then as it starts to overlap, then you start to have the dot and the sum going together to create this slope, right? And then when it's fully overlapped, you've got 1.1, 1.1, sum them up, you've got 2. And then as you're coming off the end here, just one overlap again. So that's convolution. And basically, a high-level way to think about convolution is it measures the agreement of signals. When you have convolved two signals that look very much the same, it really peaks up. And if you convolve two signals that don't look very similar, then you get less peak. And so the biggest application of convolution that you're probably all at least vaguely familiar with is FFT. And I always like to start with this before I talk about wavelets because it's easier to compare them and it's sort of a point where people are familiar. So an FFT is basically a bunch of convolutions. So my diagram here, you could think of, I have this time domain signal, and then essentially if I was doing it discrete Fourier transform, right, I would actually convolve a low frequency sine wave, and then another step, getting up to the highest frequency I'm interested in. And then you can see here, this particular signal has 3 peaks. So it convolves well with those 3 sine waves. And so you get those peaks there. The fast version of this is just some trickery. You basically don't get to pick the exact frequencies, but they're evenly spaced, and it's power of 2, but essentially it makes it go a lot faster with this trickery. Now, again, this picture on the left is just a power spectrum for the entire time of the signal. If you want to do this over and over, so basically I'm going to slice up my time windows and do, what is the frequency content at this time? What is the frequency content at the next time? That's a spectrogram, or sometimes it's called the short-term Fourier transform. And that generates a 2D output instead of a 1D output. So then what is a wavelet in comparison to a Fourier transform? So a wavelet you could think of as, I'm just going to take one of those sine waves and one of those bins and convolve it. But instead of it being a pure sine wave, it's a very specifically designed kernel or filter. And it's a huge world. We have, I think probably, 20, 30, 50, maybe pushing 100 wavelets in studio to choose from. And this is probably not even all the ones that exist. So they all have different trade-offs and things they're good at and not so good at. But essentially, at a high level, all the wavelets are trading off information, whether you get very specific information of the frequency content, in which case you give up the information on the time of when these signals are arriving. So in my diagram here, you can sort of see one wavelet might give you a really fat little frequency. Like, I don't know exactly what the frequency is. It's somewhere here, but I get very good resolution on the time. And then the other wavelet may trade off the other way. Like, I'm going to know very specifically what the frequency is, but I'm not going to know exactly the time arrival of the transient, right, of this pulse. And so speaking of that, right, wavelets are good for transients, and that's where you see them used a lot. And so if you don't have this nice continuous wave, if you have like these pulses, then you sometimes see wavelets being used for processing. And so we can take this concept a step further in studio, and we can do what's called wavelet decomposition. So the idea here is, okay, instead of just convolving with one wavelet, let me do a few wavelets so I can sort of combine it. I can get some really good frequency information and some really good time domain information. And so basically at each level, what you're doing is going up through a like essentially like a low pass filter and a high pass filter. And so you're getting high frequency and low frequency, and then you keep splitting it. And so then we do this for you, luckily, in studio. So here's our setup. And so right here, we're going to do 7 of those levels that you saw before, and we're going to do the DB3 wavelet. And what we're going to end up happening here is we're going to take statistics on those wavelets, right? So at each of those levels, we're going to take statistics on the output. And I'll show that again in another slide. But from the data set, let's take a look at it. It looks like it's clustering pretty well. There's some overlap, but it also looks like it's separating. So these different colors are different classes. Remember, we have normal, arrhythmia, and heart failure. If you're familiar with Studio, our pipeline looks like this, but if you're not, let me show it to you in just a basic flowchart. So essentially, each sample is 2 minutes long from PhysioNet. I don't know the exact number of samples, but it's something on the order of like, for our subset, we have 3 or 4 hours in this project. We elected to take that into 20-second samples. So this choice is basically a trade-off of how often I need information. So if you need something really real time in the real world, you might choose like every 1 second. But if you have more time, then obviously you've got more information to work with. So sometimes bigger windows can lead to better accuracy. So we are doing 20-second windows. Studio is going to extract that, but we're not going to do back to back. We're actually going to overlap them. And so the overlap is nice because it basically lets us get more training samples out of the same amount of data. So we're basically just sliding that window 2 seconds. So the next window is 2 seconds of new data and 18 seconds of previous data. This can also help with the classifier not getting hung up on the position in the window of certain transients, right? If you collect a bunch of data and the little pulses are always like right in the center, then doing this sliding can sometimes help with that. Then we're going to do wavelet decomposition. And like I just said earlier, for each of those levels, we're going to collect statistics like peak, skew, RMS, and that's going to give us just a flat array output. So we're looking at about 100 samples, and then we're going to feed that into a dense neural network, so just fully connected. And then final layer is a class prediction. So, but really, what's the high-level takeaway of all this? Dimensionality reduction. We're taking 10,000 points, right? You've got 20 seconds at 500 hertz. And so we're taking that and turning it into 112 points. So orders of magnitude less data per sample that the classifier has to deal with. So now let's turn it around. Let's talk about the case if we don't have any DSP. And it's totally doable, right? Obviously, image classifiers deal, and object detection network deal with these massive photos, 3 channels, could be 300 by 300, 1,000 by 1,000 pixels. So it can be done. Same thing for time domain. And I mentioned images specifically because the way you would a lot of times deal with a large input like this is just like with a large input, you use convolutional layers in order to avoid the model blowing up in size. Same thing, we just do it in 1 dimension. If you're familiar with Keras, I put the sequence up there on the right, but just to talk through it, essentially it's just like the convolution we talked about for DSP. So you're sliding this filter and multiplying and summing it up, and you just keep moving it. And the only difference here is for wavelets, right? That's a pre-designed kernel. Pre-designed weights is another way you could think about it. We don't typically call them weights in DSP, but that's essentially what it is in machine learning. The same thing. It's the values of the kernel. And so like most convolutional networks, we have this set up where we're going to have first layer 64 filters. So you basically get to design, it's going to learn 64 different patterns to convolve that are, hopefully useful. Next layer is 128. So you're max pooling, so it gets smaller, but you get more filters, so more chances to figure something out. And then a final dense layer where you're basically looking at the features you extracted with your convolutional layers and trying to cluster them and figure out what the classes look like. So with that said, how did they compare? So these are all screenshots from Studio. First one, we'll start with the good news. Both did pretty well. The DSP's on the left, 95%. Confusion matrix pretty reasonable. The convolutional did pretty good as well, just a few points back. And honestly, if we played with that network more, maybe shrink it down because maybe we don't have enough data to train that many weights, or maybe it needs more convolutional layers, or there's things we could have done. We probably could win those 3 points back. So from an accuracy standpoint, they're both looking good, but that's where the good news ends for the convolutional network and raw data. So let's start looking at the footprint or the amount of resources you're going to need when you deploy this on device. So I've got the 1D conv on the top, and then at the bottom where it says with DSP is the same model. And again, if you remember a few slides back, the model we attached to the DSP was just a simple, fully connected. So it was, I believe, 20 nodes and 10 nodes. And then a final layer. So pretty typical MLP, just a simple classifier. And as you can see, that really pays off because we're an order of magnitude difference here on both RAM and flash. We're talking megabytes of RAM and flash for the convolutional network and kilobytes for the model attached to the DSP. Now, just to not, slide anything under the rug here, you might be saying, well, the DSP has overhead. Yes, that's what this next slide shows. One thing, the DSP didn't blow up the processing time, only 69 milliseconds. The convolutional model takes 1.5 seconds to run, and then only 100 kilobytes of RAM. So we're still in the kilobytes RAM. We're getting nowhere near 3 megabytes of RAM. I don't have the flash usage modeled from Studio, but I know that our wavelet code that you can compile and deploy with is on the order of like tens of kilobytes, maybe 100 kilobytes. So again, we're nowhere near that 3 megabytes we saw with the convolutional layer. And so that's typically where the conversation around DSP ends, is it's more efficient. But another thing that I think gets overlooked a lot, and I wanted to highlight here, is that it's a smaller model. That also means you need a lot less data to train it. And typically the way that pans out is I have a small data set, I try to train it different ways, and it doesn't work, or it only works with DSP. But this was an interesting use case in that this ECG set is quite large. So we actually do have enough data to make the convolutional network converge. So we're proving that, convolutional can work. We made it work. It just took a lot more data, and we can even quantify that. So what I did is I actually trained with subsets of the data set. And so on the bottom here, I have number of samples. So the full set was something like 3,000 windows. And they both converge pretty quick. It's a pretty forgiving data set. So they're both starting to do better together around 500 samples. But look on the early samples, like right here at 128. We're getting like 25 points better performance almost in accuracy of wavelet versus convolutional with only about 100 samples. So this is, to me, actually, I think the biggest benefit of using DSP for feature extraction. And I say that because when you talk about hardware footprint, everyone always wants to reduce COGS, right? Let's ship a smaller processor. So smaller footprint is good, but at the end of the day, you can always throw hardware at the problem. But this is a problem that DSP solves, that you can't just throw hardware at the problem. There's a lot of times where you're in a situation where you cannot collect enough data to train a really large convolutional model. Either it's prohibitively expensive or the data just doesn't exist. Like you just don't have access to it. It's hard to get to. And so by using DSP, you can get good accuracy with, sub 100 samples sometimes. And that's just not really feasible with a convolutional model over like a 10,000 point input. So Yeah, to summarize, I always recommend with time series, try feature extraction. It could just be simple statistics, but DSP can be especially powerful. All of the blocks built into Studio are very turnkey, easy to use. We even have an auto tuner, so it can pick all the settings for you if you're intimidated by things like, well, what's FFT size and how do I pick that? And then, of course, all that we have very performant, low footprint versions that run on device. And this will let you train with a lot less data and get a successful model and obviously reduce your footprint significantly. So, thanks for joining me today. We'll go to the questions now, but I hope you enjoyed it and I hope you try some DSP with your next model. Thanks a lot.